Euler's formula. Why is that so significant, right? Do you remember how to prove Dumas theorem? I'm gonna give some space and go down here. What was Dumas theorem? Oh, come on, people. Cosine theta plus I sine theta to nth power. Okay, I'm not really putting r here because that's r to the nth power. That part is obvious. Somebody tell me how this thing works out. Oh no. Cosine. Really? Right. Now, how do you prove that? And this is the thing that you call CIS, right? And this n is as if you multiply to the angle. So when you take powers of complex number, it spirals out like that. Have you seen that picture? Right. And this is the shape of a snail. I mean, this is a naturally occurring thing. Well, how do you prove such a thing? Have you at least proven this with induction? Oh, you haven't. Maybe I should have put that on the. Okay, this is calculus, not pre-calculus. So consider yourself lucky that I was not your pre-calc teacher, because I used to put this on the test all the time. It's not that hard, but we are not going to really prove this with the induction. Today, we're going to prove this by proving Euler's formula. Okay? So let's just say, so what this Euler's formula is saying is this is same as CIS theta. You know what I'm saying? This part. Really? How is it? Here we go. Okay, proof. E to the ix. I'm gonna back off. What's the e to the x? Maclaurin series, Taylor series. 1 plus x squared x plus x squared over 2 factorial plus x cubed over 3 factorial plus like that, right? Say yes. So what happens if we are microwaving this? Put I theta here. I just replace all the x with I theta, right? Well, so I'm gonna write it. As a proof, so we can afford to write a few more lines. Good. Okay. 1 plus I theta plus, what's I squared? Somebody tell me what I squared is at least. -1. -1. So we have theta squared over 2 factorial. Somebody tell me what I cube is and keep it coming. Oh, come on. Negative I. Let me put it up here. So theta cube over 3 factorial. I to the fourth?
1.
1. Fifths?
I.
Let's write 2 more terms. 6th? My God.
-1.
-1, thank you. One more, please. Somebody spit it out. 7th?
-I.
-I. And Okay. Wow. So we have real and we have imaginary terms, right? Shall we put them into real and imaginary separately? So real part, 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial, right? Minus theta to the 6th over 6 factorial, dot, 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 plus I common factor, and let's put all the I terms, imaginary terms. So we have theta minus theta cubed over 3 factorial plus theta to the 5th power over 5 factorial minus theta to the 7 over 7 factorial, eh? Now, please tell me you recognize this thingy? After doing your homework, what is this first real term?
Cosine theta.
Cosine theta. And this thingy with I? What is that thingy? Odd term.
Sine theta.
Sine theta. Oh my God. We're done. E to the I theta is equal to cosine theta plus I sine theta. Whoa. Whoa. Whoa, 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 whoa. That's impressive now, isn't it? Okay, this one I'm going to actually put it as, this is so annoying, corollary. What is a corollary?
Extension of a theorem.
Yeah, maybe theorem, right? Okay. Okay, so corollary. Okay. I'm gonna apply this thingy. So this thingy is equal to e to the I theta to the nth power, correct? Say yes. Say yes. Okay,
Yes.
This is equal to rule of exponent, right? So e to the I n theta, eh? Say yes.
Yep.
Now we use Euler's formula back. So we have used the Euler's formula here. And now we are going to go back to cosine and sine format, right? So look at n theta as a theta itself. And then that is cosine n theta plus I sine n theta. Whoa, there you have it, the Moab's theorem. That's why when you take these powers of complex number, the angles add, therefore you rotate and spiral. The other coolest thing, and this is the coolest thing there is, this is famous equation. What are the 5 most famous historic and naturally occurring constants in the universe? I'm going to give 0 first. I mean, okay, let's go in historical order. I think 1. Humans have discovered 1 before 0. Actually, it took humanity quite some time to figure out that 0 is a number, right? And then next one is, somebody said it, pi, right? Ratio to a circumference to the diameter of any circle in the universe. So if there's a space alien, right, coming here, landing in the lawn of Peninsula High, let's say Southward Field, they are not, okay, there's a thing about Hollywood people. Usually there will be liberals going out, oh, are you coming in peace? We welcome you. We open our planet to you so we can coexist in peace. We are supposed to, after all, you're supposed to accept all the aliens, right, of any form. What? I'm talking about space extraterrestrial here, disclaimer. And then they come and they talk to you, or, right? Okay, there are a couple of things that's wrong with this. Number 1, they will not speak English. Hollywood thinks that English is the universal language of the universe. It ain't, okay? Many of us, or at least our parents are from another country and they don't speak English there either. So it's like, come on, space aliens will not speak English. Let's not assume that. Number two, they may not come in peace. They, for all purposes, they might view us as food. Right? So let's not assume that. But one thing is for sure, they know the value of these constants, such as pi, as I'm pretty sure their planet still looks spherical, and they have figured out that ratio. You know what I'm saying? If they have enough technology to make space flight, they should know these things. And what's the next one?
E.
E, of course, that's a naturally occurring phenomenon. I told you the definition of E. Somebody give me the last one. I, right? I is a natural constant, square root of -1. And I like to add one more from physics. These are 5 mathematical ones, but there's one more that's coming from physics, and that's a big deal in space flight, especially if they're gonna make that trip and without dying in the process, in that journey, because they're hundreds of million light years away. Oh, come on, people. Speed of light. Okay, because there's an ultimate speed limit in the universe. But not just, let's just look at this, that what we get from mathematics, okay? Somebody tell me the value of this thing that I'm gonna write down. E to the I pi. What is e to the I pi according to Euler's formula, we just proved? This is cosine I pi plus I mean, this is cosine pi plus I sine pi. So what is it?
-1.
-1. So if I add 1 to it, we should get 0. Well, this neat little equation has all 5 of this natural constant in it. Isn't that great? All 5 of them are related to each other in this manner. Dang, huh? Okay, maybe it's not as amazing to you as it was to me when I first saw it. Fine, okay, let's prove Cauchy's theorem. Nothing impresses kids these days anymore. Okay, Cauchy's theorem. Actually, I'm gonna change the color. Where's my mouse? Here's my mouse. This computer is not responding to me. It's gonna crash now. Oh, come on. What's going on with this thing? Does it write? Oh, okay, it writes. Does not want to erase? Oh no. So I have to prove this without screwing up, huh? Okay, I guess. Does it? No, it doesn't change the color. It does not want to write. I mean, it does not want to erase. Okay. Cauchy's theorem is called extended version of mean value theorem. So now then we have to review mean value theorem. Okay, what was mean value theorem? If G is, let's say if, oh, now it changed the color now. If G of X is continuous and differentiable, right? which is really redundant because differentiable includes continuity, right? Continuous, mathematicians always say this way, continuous here and differentiable here. Because, you know, you cannot really, one-sided derivative is not really a derivative, you know what I'm saying? So continuous all the way up to the boundary and differentiable here. And let me draw it. So what that looks like, because the picture is what's more important. So say our G looks like that. And this is the point, endpoint, okay? So this is point A, and this is point B. You know what I'm saying? So this is f of A, and this is f of B. Okay, then there exists C such that G prime of C is equal to the average slope. Did I write F? I call this function G, and I do that for a reason. Minus G of A over B minus A. Okay, this is known as mean value theorem. And many MBT, a lot of mathematicians say that MBT stands for most important theorem. I disagree. Taylor's theorem is most important theorem. Fundamental theorem of calculus, #1, and Taylor's theorem, but I mean, they love this one. They're obsessed about this. And they actually in analysis, this is a big deal. They use this a lot. Okay, and I kind of know why they are obsessed over this. Okay, good. So what does it look like? If you draw the line segment, so that's the average slope. There has to be at least one C where this thingy derivative is same value. So it's that tangent line is parallel to that secant line. This is known as C. So in this very picture, there are two C's. Okay, that's the mean value theorem. Good. Good, 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 good. Okay, Cauchy's theorem looks very similar to that, but it's actually extended version. Cauchy's theorem. And this is what it states. For two functions that are continuous and differentiable, so let's say g of x and h of x, right? Continuous, let's say on a and b, A and B, and differentiable derivative exists on open interval A and B, because derivative is a little bit trickier. That's what they mean by continuous and differentiable. Otherwise, they would have just said differentiable if it's just parentheses, not including the endpoint. Because we are using the endpoint, you see why this is kind of a big deal, right? Okay, now, then, I'm gonna say there is C such that, now here's the content. G prime of C over H prime of C is equal to G of B minus G of A over H of B minus H of A. What? Is it even remotely believable? The ratio of the two function derivative? You see, let's compare that with mean value theorem. Mean value theorem, this is x-axis, so this is G, the y-axis, so yeah. I mean, that's kind of believable. But is this even believable? Ratio of 2, change it. Why is that? right? Let me give you a picture of what it looks like. So maybe like this thing over C, this, no, it's not even that imaginable. So here's a picture. Okay, so this side is the g of x. This side used to be x, but I'm going to put h of x now. Kind of like parametric plane. You know what I'm saying? It used to be x and y, and t was your independent value. So x is your independent variable, and this is h and g. Okay, and likewise, this function, so this could actually go in any direction. This doesn't need to be a function, but in order to make sense, I'm going to draw as if they are function. Okay, so this point right here is h of a, and this point right here is h of b, and this point right here is g of a, and this point right there is g of b. And the exact same thing applies. So if we draw the line segment, connecting these two like that, then there has to be C where these are parallel to that line segment. Okay, so this will be h of C then. You know what I'm saying? Really? I think we need to prove this, right? Yeah, we better, because this is not even remotely believable. Okay, let's prove it. And many times in math, you have to come up with something clever function. And this is a clever function. It's not like I expect you to be able to come up with this on your own, but you need to see this at least once in your life, okay? This is big deal. Ingredient we need, g of b minus, and I didn't come up with this. I read it somewhere. Okay, that is constant, all of it, right? Kind of what we need on the numerator in this theorem, times h of, and this is the clever part, x minus h of a. So that's the denominator here, except instead of b, I put the variable x. Good? And then minus, okay, I'm going to, running out of space. Minus, and then I'm going to put g of a, oh no, not the g of a, g of x, minus g of a. So kind of same thing as this, except now I put x here instead of b. And h of b minus h of a, which is same as this thing. Okay, right? Like, why would you want to do such a thing? Here's the motivation. Then g of a. What is g of a? If I plug in a here, I mean z of a. If I plug in a here, that's h of a minus h of a. So this term is 0. If I put a here, then g of a minus g of a, that whole thing is 0. You know what I'm saying? So this is 0. Good. Now let's calculate z of b. What is that? If I put b here, then this entire term, and if I put b here, this entire term, they look exactly identical. So something minus itself is also 0. Okay. Now, mean value theorem applies to this function z. Okay? I'm going to sketch this function z. Whatever the hell this is, it's going to look like this. They're both 0 here, and maybe it looks like that. They have to connect. Z itself is a differentiable function, isn't it? Because if you multiply two differentiable functions, you get differentiable functions. Well, then there has to be C. This is known as the Rolle's theorem, right? The primitive version of mean value theorem. There is a C where this tangent is parallel to this. So now by Rolle's theorem, how do you spell Rolle? I think like that. Or mean value theorem. There is, this means there is C such that, that C has to be in between A and B, right? Such that, yeah, there has to be a C between A and B. Z prime of C is equal to 0, right? That slope, derivative of the tangent line, has to be parallel to this line, secant line. You know what I'm saying? You with me? Okay, let's just write down what that means. So my Z is here, right? Okay, so Z prime of C, right, is equal to, well, Z prime of C is equal to 0. Implies, okay, I'm going to put how should I write this? Yeah, I'm gonna just substitute it. So this is constant. I'm gonna copy and paste. Hopefully that'll copy. Let's put it here. Good. It worked out. Okay. So what it says is, whoa. I'm gonna put it in the line below because that's kind of long. So that implies this. I'm going to take a derivative of this ODE, right? When I take a derivative, this is constant, so it's the derivative of this minus derivative of this times that DE, right? Derivative of this itself is 0, so this part is gone. And then this becomes prime. Good? You with me? You with me? If I take a derivative of that whole thing, this is the only variable. So this one constant term dies and you just still multiply. Likewise, this thing becomes prime and this thing dies, right? And this thing is constant. Let's clean that up, shall we? So what we have is this. There. This is equal to 0. Good. That's the derivative of Z. Now we are substituting C instead of X. So now this becomes C. Still with me? Now, instead of equal to 0, we can actually bring that one to the other side, so make this the equal sign. Good. Say yes. I'm gonna divide both sides by this. So now on the left-hand side, it becomes G of B minus G of A over H of B minus H of A. Good. I'm going to also divide both sides by H prime of C. So I have G prime of C over H prime of C. Wow, why does that look so familiar? Because that's what we set out to prove in the first place. There's your cautious theorem. Dang, huh? Right. Now, like I said, really I don't expect you to be able to pull this off, but this is a handy ingredient that I'm gonna need, okay? So before we say goodbye, finally, I kind of need this one a lot. Really, I'm gonna write it in terms of this numerator. So multiply this one over there. So it's like just dividing that line by h of c. So what I have is g of b minus g of a is equal to g prime of c over h prime of c times h of b minus h of a is what I really need. But one last thing, instead of b, I want to have this thing in terms of x. This is the ingredient I'm going to need when I prove Lagrange remainder. And remember that C here was between, C was between A and X, correct? Oh, A and B, correct? So likewise, my C here now is between A and X. I'm going to need this as well, because I'm replacing B with X. Good. Today we are proving the Lagrange remainder. Okay, that formula we've been using for the last couple of days now. Okay, it's not that I expect you to be able to pull this off, but you should at least see this and understand it at least once in your life. This is one of the biggest theorem in mathematics altogether, okay? So let's review Cauchy's theorem, right? We did the proof the other day to save this time. So the Cauchy's theorem is kind of like mean value theorem, except because in a mean value theorem, and my computer is not cooperating and zooming in, see, you have nothing here, and then you have just b minus a here. But I have it against another function. So between two functions, this is parametric window, g and h, x is not shown. So there's gotta be some kind of curve. And that slope of that curve is still, there has to be at least one point, we are calling it C, between A and B, that's the key, between A and B, that is parallel to that secant. Okay, so this is Cauchy's theorem, and I have proven it with a nice little gimmick by creating this, and use the mean value theorem, or also known as Rolle's theorem if these two are the same, and we arrived at that, but more importantly, this is what I need. So if you buy this, I just multiply this denominator to the other side and then replaced b with x, so it becomes a function. So since the c was between a and b, now my c is between a and x, and that sounds a little familiar. Lagrange error, c is between a and x. Good. Any question about Cauchy's theorem before we proceed? Okay, we will move on to proof of Lagrange remainder. Okay, first thing, f of x, we are finding the Taylor series representation, and that looks like this. A naught plus a1, I'm going to zoom in a little bit, and then x minus, we are using a as a center, and a little confusing because c is something else, so now, so plus a 2 x minus a square plus and dot all the way to an, and then x minus a to the nth power And this is what we are calling P sub n, correct? This term is P sub n of x. Good. So we have f of x here is equal to P sub n of x. And then we have a remainder term. Okay, so that starts with a n plus 1. That's why Lagrange error starts with n plus 1 term. And x minus a to the n plus 1 n plus dot dot dot. Okay? And this, for the rest of the eternity, is r sub n. Good. So far with me? So your f of x is P sub n plus r sub n. Good. Which means I can write now r sub n of x, like kind of I explained it in homework, f of x minus P sub n of x, correct? I just move it over to the other side. And what it states is this whole thing, the Lagrange error, can be written as f and then n plus 1 derivative evaluated as some c between your center a and x, and then n plus 1 factorial here. Okay, x minus a n plus 1 power, and then for some c, and c is between a and x. Good. This is the statement of Lagrange error. Are you with me? Okay, then let us prove it now. So here's proof.
Is there an absolute value?
Technically, no. We usually put absolute values to say error because this could be a negative term, but f of x is just p plus r, isn't it? So r is equal to f minus p, and this could be negative, right? Your error could be negative, but when we say error, I mean remainder could be negative, but when we say error, we don't like negative errors. That makes it sound right, so we just put absolute value around it.
So this is just the remainder, not the error.
It's just the remainder. Okay. Then so that remainder term could be positive or negative, because your function could be positive or negative at any point, right? But when we say error, there's no such thing as negative error, so we always put absolute value around the errors. Okay. Let's remind ourselves what this formula is, which you're not allowed to use on the test. But your Taylor series formula, you evaluate it at your center plus f prime, and this is where the formula comes in handy because we have to do proof 1 factorial, and then x minus a to the first power, and then f double prime of center, and 2 factorial, and then x minus a square plus, let me write one more term, f triple prime of a over 3 factorial, and then x minus a cube plus dot dot dot, and this will go on all the way to nth derivative evaluated at your a over n factorial, and then we have x minus a to the nth power, correct? That's the Taylor series formula that you're not allowed to use. Okay, now, then I will, this is a nice trick. I will create a function g, and g is a function of t, okay? And that thing is almost same as what we have here. So this is f of, instead of a, we replace it with t. That's the little trick. Okay, this version of proof is a lot shorter, but then it requires this trick. Okay, plus f prime of evaluated at t over 1 factorial x minus t plus f double prime. I'm going to zoom in so you can see better. T over 2 factorial and then x minus t square plus f triple prime t over 3 factorial x minus t cubed plus dot 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 plus all the way to the end, and then f nth the derivative evaluated at t over n factorial, and then x minus t to the nth power. So far it's just a definition. Well, like mathematicians do this a lot. Within the proof, they just define a function. Okay. Remember when I was doing Lagrange proof, I mean the Cauchy's theorem, we came up with this clever function called z, and that function actually made a difference for us, right? So it's kind of like that. So it didn't happen overnight. I mean, it took some mathematician long time to construct such a function. So if you cannot come up with it, don't feel too bad. Okay, most people cannot come up with it either. Okay. Now then, a couple of things we need to note. Okay, let's note a couple of things. What is g of x? What happens if I replace all of these t, because g is a function of t holding x as a constant, okay? Where p is the polynomial function of x. So there's a little subtle difference, right? This is almost like multivariable calculus, but you can view one of the function as a constant. But if you plug in x here, then this thing becomes f of x, correct? And then this becomes x minus x, 0, x minus x, 0, so the rest of the terms all die. So g of x is designed to be exactly same as f of x. Remember that z at 0 and at a and at b, it becomes same thing, so it's kind of like that. Okay, another thing that I want you to note is, what is g of 0? I mean, not 0, g of a. We constructed this g from this, isn't it? So once you have a, then that is just exactly Pn, correct? Are you with me? So far so good? So then let's review what R is, right? Our R's of n of x. Remember from up here, right there, R is f of x minus Pn of x, correct? That's by definition of what remainder is. And f of x is g of a x minus Pn of x is g of a. So far, so good? So far, so good?
Yep.
And in case you're wondering where the heck this is going, g of x minus g of a, g of x minus g of a. That's where it's going, okay? That's why I needed this. So we are eventually using this right-hand side. So here, g of x minus g of a, well, we need g prime, right? And we still don't know what h is, because that's another clever function I'm going to construct. But we at least need g prime a. Okay, so let's go ahead and find g prime, shall we? Yes, we shall. And this is another really clever construction. I'm going to use all different colors. So g prime of t. So since it's a function of t, I'm going to differentiate it and substitute c. Okay? So g prime, let's see, g is up here. So we have f prime of t. Okay, plus product rule here, right? Suck it up and do it. So this thing, f double prime of t times x minus t minus, because the chain rule will make it minus, and then f prime of t -1, right? This thing, because with the differentiating with respect to t, it gives you -1. Good. That's for that term. I'm going to do the next term, plus f triple prime of t over 2 factorial x minus t square, and then this will be minus f double prime of t over 2 factorial, and then derivative of that will be 2 x minus t square, and chain rule will make this thing negative. So far, so good. Are you with me? I know this is a little confusing, but it's the chain rule of this term. I mean, the product rule of
But
this
why is
term.
it still squared?
Because I forgot.
Okay.
There. Nice catch. So far, so good. Okay, we're going to do this term now down here. So we'll have plus f fourth derivative of t over 3 factorial, and then x minus t cubed, and this will be minus again because of the chain rule, f triple prime of t over 3 factorial, and then we'll have 3 times x minus t squared this time. I got it this time, and then chain will make this thing negative. Good so far? Then we'll say dot dot dot, and then we'll do the nth term. So we have f of n plus 1 derivative of t evaluated at n factorial and x minus t to the nth power minus product rule. So f of n derivative at t n factorial, and then we have n times x minus t and minus 1, and then negative sign. With me? Anybody lost? Okay then. God, how good are your eyes? If I zoom out, can you see anything? Because my eyes cannot see this. I'm gonna move this slightly so that at least it comes into that one page. Okay, now let's notice a few little nice things here. Here, this cancels this, right? So far, so good. Do you see they are opposite terms? Okay, let's see this term right here. This 2 cancels that 2. Then what we have left is f double prime t x minus t, which is exactly the same thing as this with a minus sign. So this whole thing cancels that whole thing now, right? Whoa, what's going on? I know this is a clever construction of function g, which is the highlight of this proof. Okay, now let's look at the next one then. This one right here. This 3 cancels this and makes it 2 factorial, correct? Well, then you compare this term to that term, and they are exactly identical with a minus sign, so this whole thing cancels that whole thing. This is like collapsing series. It's designed to do that, and everything cancels out. What is the only, I mean, not everything cancels out, everything except 1 cancels out. What is the only term remaining? This is the only term that survives, and this is going to cancel whatever's before here. Dang, huh? That is shocking now, isn't it? So g prime of t, I'm going to write it down here. Therefore, g prime of t is equal to that thingy. F at, and oh, here we go, n plus 1 derivative evaluated at t over, still n factorial, so we are not quite there yet, and n minus t to the nth power is something we are going to need. You with me? So far with me? Okay, here comes another nice and clever function. Once again, it took some mathematicians some time to construct these things, so don't feel too bad about it. If you cannot come up with one, you're not a mathematician yet. H of t, once again t, x minus t to the n plus 1 power. Don't ask me how they came up with it, okay? They just work with this over and over to get what they want, okay? So that's a nice function. Now, let's see what h prime is. Because h, why does h ring a bell? That h right there, you get it? That's the h. And so I'm gonna need h prime. So come back, so h prime of t is the variable here, so do you see it will be x minus t, so this n plus 1 comes here, and then we have n's power, and then chain rule, we'll put negative sign in front, right? You with me? Are you with me? Okay.
Yeah.
Now I have all of the ingredients and all the meat and everything. Remember this theorem? I'm gonna make a copy of this theorem. Let's go down here and paste it. Now I'm ready to use this theorem. Okay, so that's from Cauchy's theorem, and I'm going to substitute everything, okay? You ready? Should we change the color? Let's go back to blue. Okay, so this g of x minus g of a now is, this g prime is this thingy, right? Except we need c, because some c, because as long as this Cauchy's theorem applies to all functions, any g, any h, right? So I'm using that g and this h here. So all I have to do is just replace t with c. Good. So I would have f n plus 1 derivative as some c, and that c happens to be between a and x over n factorial x minus t to the nth power over, that is g prime. Now I need h prime. H prime is right there, negative n plus 1, and then x minus t to the nth power. Good. So for, oh, t.
Is it x minus c?
X minus c, I just noticed it. So far so good. And then you can already see these two will cancel, right? Which is nice. It's designed to do that. Does this negative sign make you nervous? Well, let's see. H of a. What is h of a? Well, we plug in h of x, right? H of x. We plug in x here. That's 0, right? Do you see that? Do you see that h of x is equal to x minus x to the n plus 1, right? Which is 0. Okay, minus h of a. Well, all I have to do is just substitute t with a now. So I will have x minus t, a, n plus 1 power. Good. Say yes. Do you see it yet? Well, this negative sign cancels that negative sign now, right? Oh my God. So what we have is f n plus 1 evaluated some c, over, okay, how do you simplify this factorial and this? Is it just n plus 1 factorially?
Yeah.
This is n plus 1 times n factorial, which is this. Negative signs canceled out. X minus a to the n plus 1 power. And this is Lagrange remainder as you know it. My God. At the end of the proof like that, in the past days, mathematicians used to write, it's been proven. It's Greek. God, I forgot what it stands for, but like, what? Okay, I'm not gonna even try to speak Greek. Or these days, they put something like this and fill it. This is a new favor these days. This or this. You need a statement like done.